Hello everyone. So we need to detect a sequence 110 going in this direction. So 1 then 1 then 0. And first of all, what do we mean by that? So we need to detect it using a digital circuit. What that means is that at some point we will have a wire that is an input. This is the input. And when we say 1, it's like 5 volt on this wire. And when we say 0, it's somewhere around 0 volts. So this is our input and it needs to go in somewhere, and this is our output here. And whenever we see 1 then 0 from our input, we're going to have here 1, which means like 5 volts. So if we have like a light here, it will light up. So first of all, how do we even know when there's one state and another state and the third state and so on? We cannot just have wires connected together like in a Boolean circuit and that's it, or whatever it is, because the wires here are the same values at all time, or if we change them, it will not be based on a uniform states. Like we will not be able to say this is the third state or the fourth state or whatever it is. This is why we need something with a clock. So there's something called flip-flops, and the simplest one is the D flip-flop. So D flip-flop, and what this has is a clock. So this is the clock. What we mean by a clock is that it has basically a frequency and a period in which it switches at every period. So whatever the input is, it will be the output as well at that moment. So let's say this is our time and our period is the same every time. So this is where things are switching, and we put 0 here during this part here, and the output will not be 0 until we hit this clock rate. So until here we will see 0 for the output, and during this period, during the period here, if we switch the input to 1, we will not see it in the output unless the clock hits, and we will see an output of 1. And if the input stays 1, we will also see input of 1 or output of 1. If the input changes to 0, we will see an output of 0 at this clock rate. Every time it's the period of the clock, whatever is on the input will become at the output. So this is a basic flip-flop. It takes the input and puts it in the output at every clock rate. So we're going to use these D flip-flops to design our circuit, in which we have basically the input, and from here somewhere from our circuit, so if we look at our circuit as a black box, from our circuit, whenever we see the 1, 1 and 0, so basically if we're looking at this time plot, we will be seeing something like, let's say these are our clock rates, the periods. We will be seeing 1, 1 and then 0. So every time, let's say this is also our output. For our output, it will have the same frequency for the clock. So for here it will be 0 because we haven't met our sequence yet, detected our sequence. This will also be 0. And then here when we hit our sequence, it will jump to 1. This will be the output here. And then if it happens again, 1, 1 and 0, the output will be 0 for the first 2 clocks rates, and then it will jump to 1. So this is what we mean by our circuit. This is what we want to achieve here. If we see such input like this, we're going to see such output like this. So whenever we hit our sequence, we detect our sequence, we're going to output a 1. So we're going to start first with something called state diagrams to represent our states. Basically, every state in our state diagram will represent something that we have seen in our sequence so far. So we're trying to detect 110. So is the first state will be whenever we have seen absolutely nothing. So it will be, we'll call it as 0, and this, what we have seen so far is nothing. And the output here will definitely be 0. We have not seen our sequence yet. So this is the first state. The second state is when we have seen the first bit of our sequence, which is 1. The output will also be 0 because we haven't seen all our sequence yet. And the third state will be when we have seen 1, 1. Also the output is 0. And the final state would be when we have seen all our sequence. And this is the only state in which the output will be 1 because we've hit all our sequence. So now we want to build this state diagram. By state diagram, we mean that at every state, depending on the input, where are we going to go next? So if we are in state S0, which means we haven't seen anything, and we only have two options for the input. This is binary, so we only have 0 or 1. So if we see a 0 for seeing nothing, we will not go to any of these because by seeing 0, we haven't seen 1 or 1, 1 or 1, 1, 0. So we're going to stay in S0. If we see 1, however, we're going to move to S1 because now we are in the state that we've seen 1. After that, if we see 1 again, we're also going to move to 1, 1. If we see 0, however, we cannot jump to 1, 1 because we have seen 1, 0 so far, so we are back to seeing absolutely nothing because it's nothing related to our sequence. So now if we are in S2, we have seen 1, 1 so far. If we see a 0, we're going to go to S3. However, if we see 1, we will not go back to seeing only 1 because we've already seen 1, 1. So if we have seen 1, 1 so far and we see a third one, we can disregard this one and we will be seeing the past 1, 1. So we would basically be staying in the same S2. We will be also seeing 1, 1. Now from S3, if we see a 0, we will go back to the S0 because that's seeing nothing from our sequence. Basically here in S3, we already detected our sequence, so now we need to reset everything. If we see 0, it means we haven't seen anything new for the next sequence we want to detect, which is still 1, 1, 0. So we go to S0. If we see 1, we have seen our first bit of the sequence we want to detect, which is in S1, and we go to S1. So this is basically our state diagram. And from this state diagram, we can move to a truth table. So basically, to be able to design a circuit, we will need a truth table or a logic circuit. Now, how do we represent states in logic circuits? So right here we have 4 states, and in every wire that we use, it can only be 0 or 1. We cannot put 4 values inside one wire. So basically, we're going to use 2 wires. So by using 2 wires, we can have 0, 0, 0, 1, 1, 0, and 1, 1. So this can be S0, S1, S2, and S3. So whenever we put in these wires 0, 0, for example, we mean we are in S0. If we put 0, 1, it means we are in S1. We can also give them a name of Q1 and Q0. So looking at the circuit we would like to build, we're going to have, because we have 2 wires, so we need 2 outputs and 2 inputs, we're going to have 2 D flip-flops. Each one will have a clock, and this is the input, and this is the output. So this output is basically what state we are in right now. So this will represent the current state. This will be our current state, which is represented by Q1 and Q0. So if we see here on these wires, having like 0 here and 0 here, it means that right now we are in state S0. If we see 1 1, it means we are in state S3. And what we want to put here as input to the D flip-flops is whatever will be the next state after this state we are in. So for example, if we are in 0 0 here, so the current state is 0 0, and this is our input, and the input is equal to 1. From our state diagram, we are in 0 0, and the input is 1. The next state should be S1, which means it is 0 1. So whatever has to be input here will be 0 1. We can call this Q1 plus and Q0 plus, which is the next state. So how do we move from the zeros and ones in Q1 and Q0 representing the current state to the something to represent the next state? Basically, these wires are going to come here and they're going to go through a logic circuit that we will design, and the output will go to as the input to these D flip-flops, so that they will be updating the next state whenever the clock rate hits. So we're going to move from this state diagram to a truth table. Okay, so inside our truth table, we're first going to have what is the current state and what is the input and what is the next state we want to achieve. So the current state, the input can be 0 or 1. The current state is represented by Q1 and Q0, which we just talked about, which are the two wires going out of the D flip-flops. And the input, we can call it I. And the next state will be Q1 plus and Q0 plus. So now we can start writing all the possible inputs for the current state and the input. We'll start by putting all the inputs 0, 1, 0, 1. It's a good way to just like basically for the first write bit, we flip one bit, and for the second one, every 2 times we flip the bits, and for the third one, every 4 times we flip the bits. So in total, we're going to have 8 possible scenarios. Okay, so now we have all the possible inputs, and we will be able to write what will be the next states for this. So what do these mean? So if we have here Q1 and Q0, 0, 0, it means we are in S0. Same thing here as 0. S1, S1, S2, S2, and S3. So 1, 1 for Q1, Q0 is S3, and so on. Now from the state diagram, we can simply look and see how to move from whatever input we have here, for example 0, 0, 0, to what state we have to be. So if we are in state S0 and the input is 0, we're going to stay in S0 based on our state diagram. So the next state here will be S0, which means it is going to be 0, 0 output, or 0, 0 based on the 2 bits that we have, Q1 plus and Q0 plus. If we have input 0, 0 and we are in the state 0, 0, which is S0, and we have input of 1, we're going to move to S1, which is 0, 1. If we are inside S1 and our input is 0, we're going to go back to S0. So this is going to be 0, 0. Now if we are in S1 and our input is 1, we're going to move to S2 based on our state diagram, which is S2 will be, we drew them here, so in case you forget, you can always go back to here. It will be 1, 0, S2. So S2 will be 1, 0. Now we are in S2 and the input is 0. So in S2 the input is 0, we're going to move to S3, which is 1 1, and S2 the input is 1, we're going to stay in S2, which is the same as the input 1 0. If we are in state S3 and the input is 0, we're going to go all the way back to S0, which is 0 0. And if we are in S3 and the input is 1, we're going to go back to S1. So S1 would be 0 1. Okay, so now we have our basically truth table, which is telling us the wires we have. So our circuit again will be like 2D flip-flops here. Each one has the clock, and this is the input of our D flip-flop. So this is Q1 plus, this is Q0 plus, and these are the output Q1 and Q0. These are representing this current state here, and these are representing this next state here. So in other words, what we need to have here is that our circuit will actually, like, we don't usually draw the wires this way, but after we have these outputs, which represent the current states, Q1 and Q0, are going to come all the way back here. And now we're going to design what's inside here. Basically, we want something that if Q1, for example, based on the truth table, we also have the input coming in. If Q1 is 0 and Q0 is 0, so the current state coming from here is 0 0, and the input is also 0, we're going to output 0 0. So in here we're going to have 0 and 0, and so on. So we're going to build this circuit that will basically do this. So what we want to find out is Q1 plus and Q0 plus from these three inputs, the Q0, Q1, and the input. Whenever you're moving from a truth table to a circuit, what we really care about is whenever there is an output of 1. So let's start by designing the Q0 plus. We see 3 1s. So we have these 3 1s, and these ones are represented by having this input, or this input, or this input. So when we say we want all these 3 inputs so that we output 1, it means this is an AND gate. We want all 3 of them to output 1. However, we want this or this one here to be able to output 1. So this is, after we put these in AND gates, we're going to put all 3 of them in an OR gate, because we want only one of them would be enough to output a 1. So what does this mean for in terms of like a logic circuit? So Q0 plus would be equal to, we'll take the first one, we need Q1 to not exist, so that would be Q1 not, basically Q1 to be 0. We want Q0 to be also 0, so that would be Q0 not, and we want the input to be 1, so that would be the input. Now the second one will basically represent with a plus because it's an OR. The second one, we want the Q1 to be here, so we want the Q1, Q0 to be 0, so Q0 not, and the input to be 0, so input not, also plus. Now we want all 3, Q0, Q1, and the input. So this Boolean equation basically represent our part going from here, the Q0, to coming back, actually going from Q0, Q1, and the input to go back to Q0 plus. This is the equation for Q0 plus. So by this Boolean function, we can actually design the circuit here that will take us from all 3 inputs to know what is the Q0 plus. We will do the Q1 plus first as a Boolean equation, and then we will draw it. So Q1 plus will be a similar thing. We will look at everywhere where it's a 1. We have 3 1s as well. And we will basically look at the input. So in the first one we have Q1 0, so Q1 not. And we have the Q0 and we have the input plus the second one will be this one. So we have the Q1, Q0 is 0, so not Q0. We don't want the Q0, and the input is 0, also not input. And the third one will be 1, 0, 1. So Q1 is there, Q0 is not, and the input is there. So this Boolean function now is representing taking this input, and this input, and giving us as an output the Q0, the Q1 plus. So now we're going to draw what we just said here. Like we're going to draw these two Boolean functions into a full circuit that uses flip-flops. So we're going to start with our 2D flip-flops. So this is Q1 and this is Q1 plus. This is our second flip-flop. Now these clocks are the same clock, so usually you'd connect them with the same wire that going to the clock, but I'm going to not draw them now, just not confuse the drawing. So this is now the Q0 output, which represent the current state, and this is what needs to go in to go to the next state, the Q0 plus. So first of all, I'm going to assume that these wires here, the Q1 and Q0, are coming in this direction. Like I'm just going to draw wires here, assuming that they are connected. You don't really have to connect them in your drawing if you're using the same names. Basically, you are saying that these are the same. This is the same wire and they are connected. So starting with Q0, basically what we need here is we need the first AND gate will have Q1 not, Q1 not, Q0 not, and the input. This is this one here. The second AND gate will have Q1, Q0 not, and input not. And the third AND gate, so this is second gate, the third AND gate will have Q0, Q1, and the input. Now all these three are going into an OR gate, and they are going to Q0. So basically this circuit here will take us from the three inputs, which is the current state Q1 and Q0, these two, with the input I, and will give us an output what should be the next state for Q0. This Q0 plus and Q1 plus will be representing our next state. Whenever the clock hits, these will become the current state. So the input of the D flip-flop will be the output. So now we will do the same thing for Q1 plus. So the first AND gate will be Q1 not, Q0 and the input. The second AND gate will be Q1, Q0 not, and input not. So whenever we say like input not, it means that the input has so basically we are saying this is the input and we added an inverter to it. We're not drawing the inverter just to make it simpler, but you can just have all three inputs like this, Q0, Q1 and I, and add all the inverters. But just for simplifying the drawing, we are saying like Q0 not and I not, which really means there's an inverter there for the wire of Q0 and the input and Q1. So now this is the first AND gate, third AND gate, and now for the last AND gate, which is Q1, Q0, and which is Q1, Q0, and input. We join our OR gate. We join them all with an OR gate, and this will be our Q1 plus. So now these inputs, which are representing the current state, will be connected to here, and we have the input also coming in, and these are the wires we are talking about when we say this input here. They are going through these AND gates and OR gates and outputting Q1 plus and Q0 plus, which is really representing what state we're going to go to after we are inside this current state. Okay, so now we still have one more thing to do, which is deciding on the final output. The final output meaning that whenever we hit the S3, so whenever we detect our sequence, we want to output something. So we want basically whenever we are here in the current state, being S3, so we have one here and one here, we want to output a 1. And whenever we are in a different state, we want to output a 0. The reason I'm saying 1 and 1 because S3 is our state that represents detecting the sequence, and it is represented in Q1 and Q0 as 1 1. Based on this, it is 1 1. So this is a very simple, like if you want to detect it as a truth table, it can also be like this, like you can make it a truth table. For S0 it is 0, for S1 it is 0, for S2 it is 0, and for S3 it is 1. So basically what we need is Q1, so this output would be equal to Q1 Q0, and this is simply represented with an AND gate like this, where Q1 and Q0 is here, and this is the output. So we can add it to our circuit. Here we can have just a simple AND gate here and saying this is the output. And this would be our sequence detector for 110.